Hi, I've got a cold, so my voice is just a little deeper than normal, so sorry about that. Okay, in this video, I'm going to show you how to use the program for comparing two non-nested SEM models. If your models are nested, you can use traditional chi-square difference testing or fit index difference testing as I describe in Chapter 7 of my book. This is not the case if your models are non-nested. The data I'm going to analyze is from the numerical example in the appendix of Chapter 7. So I assume you've read the section of the chapter on testing non-nested models. Okay, the first thing we have to do is to go down and access the program. And it's down here, just above Chapter 8, the Vuong test in the BICCI. So I click on that. When I do, a set of instructions will appear in the description box for how to use the program. I'm not going to go through those because I'm going to show you how to use the program here. And then down here is the input box where we give programming instructions to the computer. Now this program requires the use of raw data, so I've got to go get the data file. And I'm going to click on Choose File, and I'm going to go to the folder that has the data file in it. And let me find that file. It's called non-nested.r.dat. And then this will show you the variables in the file, the names of the variables in the file. This is very important because R is case sensitive, and you need to make sure that you type in variable names when you refer to them exactly as they appear in this list. Okay, up here I'm going to tell the program where to find the data, what folder, and the name of the data. That's just repeated there. And then I go over to the input box to input information. Now the first option I have to choose is the nesting option, and that's scored 1 if the models are not nested. I'm sorry, 1 if the models are nested, and 2 if the models are not nested. In this case, the models are not nested. Now I'll show you the two models that I'll be working with, and I'll show you how I determine if they're nested or not using M+. But in this case, the models are going to be non-nested. I'm going to work with 95% confidence intervals. And the only other thing I really need to enter is the names of the variables in the two models that I'm comparing. SEM for non-nested models, the two models have to have the same variables and the same cases. And that is the case in this example. So I'm going to come over here and I'm going to highlight these variable names. I'm going to hit Control-C to copy them to the clipboard. And then I'm going to come over here and hit Control-V to paste them. And then these are supposed to be comma delimited. So I'm going to insert commas. And we're set to go. Now normally I would hit Register Input to generate R syntax, and then I copy and paste it into R, but we first of all want to determine if the models are nested. So here are the models that I'm going to be working with. This is model 1 here, and this is model 2 here. And model 1 says that the treatment influences mediator 2, which in turn influences mediators 1 and 3, and then all 3 of those influence the outcome. By contrast, the second model says the treatment influences each of these mediators, that mediators 1 and 3 influence mediator 2. Notice the causal direction is opposite from what I had in model 1. And then all 3 of those influence the outcome. And I might have fit this model to the data and also fit this model to the data, and I want to do a formal test of significance to see which model better accounts for the data. Okay, now it turns out these two models are non-nested, but I may not know that, and I have to determine that status, and M+ can do so. Now I show you the M+ syntax in Chapter 7, but I'll run through it really quickly with you here. So let me bring up M+. The procedure requires that we run two programs or two steps in order to get the nesting status. So this top program is step 1, or the first program I need to run. Here's the title command. Here's the data where it gets the M+ file where the data are located. These are the names of the variables that it's inputting. This is a convergence criteria that I want it to use. I discussed that in chapter 7. And then here's the model for model 1. M1 is regressed onto M2. That's right there. M2 is regressed onto T. That's right there. M3 is regressed onto M2. That's right there. And Y is regressed onto M1, M2, and M3. That's there. And then these are telling M+ to estimate the error variances for the endogenous variables. The critical command here is the save data command, where I'm going to be saving intermediate steps in order to conduct step 2 and to do the nesting analysis. So I'm going to save the data file for purposes of a nested test, and this is the name of the file that I want to use. You can use any name you want to. And it's going to put it in the same folder as where the input file is located. So I'm going to call it step2.dat. So I'm going to execute that by hitting run. The output I don't need to look at right now, so I'll just close that. And then I come down to step 2. Step 2 is set up the same way, except now in the analysis command, I indicate that I want to do a nested analysis and to go get the intermediate data in step2.dat. And then I give the model for the second model, the syntax for the second model. Here I've regressed M1 onto T. That's here. And then M3 onto T. That's there. And M2 onto mediator 1, mediator 3, and T, and Y onto M1, M2, and M3, and then I have the disturbance variances. Okay, so now I run that, and we're going to take a look at the output here. Let me open this up a little bit more. And I want to go down until I see the results for the nesting check. And there we have it, the nested model check. And the result is that the two models are not nested. And this is a fit function that I discuss in chapter 7, but it's not important for us now. The key result is that the models are not nested. So I know I'm dealing with two non-nested models. Okay, so let me close out M+. I'll minimize this, and I come back to my input box, and then I hit register input, and I then generate our syntax for you to execute the analysis. And normally we'd copy this to the clipboard and then open up R and paste it so that we'd execute it. But it turns out we have to do some editing to this syntax, and that's because I didn't know what your two models were ahead of time. Now, R uses the package called Vuong to do SEM analyses. So what we have to do is we have to write the model code using Vuong syntax. I have on the web page here another tab that teaches you Vuong programming if you don't know it. So you can go look at that. But if we scroll down, you can see that I have some comment lines here where I tell you use the Vuong code to specify model 1 and use the Vuong code to specify model 2. Now let me move this over here and let me bring our models back. And it turns out I've pre-wrote the syntax for the models that I'll copy and paste. So this is Vuong code. And this is model 1 and this is model 2. Okay, so here I'm regressing M1 onto M2. That's this path right here. And I give the path coefficient a name, P1. And then I regress M2 onto T, that's this path here. And I give that path coefficient a name P2. And then I regress M3 onto M2. And then I regress Y onto those three. And then I do a similar Vuong code here for model 2. So I'm just going to copy this syntax and paste it here into model 1. And then I'm going to copy this syntax and paste it into model 2. A model specification in Vuong begins with a single apostrophe and ends with a single apostrophe. And then this is the model itself. So now I've specified the two models. Let me go ahead and close this and bring this back over a little bit. And so now I'm going to copy the syntax to the clipboard. And then I'm going to open up R. And then I'm going to hit Control V to paste the syntax here. As I paste it, it will execute. Now the output is in blue. The syntax is in red. So I'm going to go up to the top where the blue starts. I had a sample size of 500 in this case. And the first results I get are for the Vuong test. Now, in order to apply the test, it turns out that the models, in addition to being non-nested, they need to have a property that is known as distinguishability. This is a very technical concept. I discussed it in my chapter, and I don't want to get sidetracked on it here. But fortunately, the output evaluates if the models are distinguishable or not, or have that key property in order to move forward with the test. So if we look at the output, here I'm going to extend this down a little bit so that we get a little more. The test for distinguishability is called the variance test, and it tests the null and alternative hypothesis. And the null hypothesis is that the two models are indistinguishable, and the alternative hypothesis is that the models are distinguishable. And what we want to do in order to move forward is to reject the null hypothesis that the models are indistinguishable. This is the test statistic that is used, and the p-value is less than 0.05. This is written in scientific notation, so the p-value is 0.0000634. And so we can conclude that the models are distinguishable, and that means that our test is reasonable. Given that, the program goes on and conducts a test of the two models. The null hypothesis is that the model fits are equal for the focal population. And the alternative hypotheses are that model 1 fits better than model 2, and that's not the case here. And that model 2 fits better than model 1, and that is the case here. The p-value is less than 0.05. So the second model does fit better than the first model by virtue of a non-nested likelihood ratio test. And we've evaluated the relative fit of the two non-nested models. Now there's a second approach that is used in the program, if appropriate, and that's to compare the AIC and the BIC, the Akaike information criterion and the Bayesian information criterion, using confidence intervals. Some people are more comfortable using these tests because the statistics are a little more familiar to people. Here we get the AIC and the BIC for model 1. And here we get the AIC and the BIC for model 2. The lower the value, the better, it turns out. and then it forms a confidence interval of the difference between the two models using the AIC statistics and the difference between the two BIC, and it forms a confidence interval around it. The confidence interval for the AIC difference, if it contains 0, then it's not statistically significant. But if it doesn't contain 0, then we can reject the idea that the models are not different from one another. And in this case, the AIC is agreeing with the likelihood ratio test and saying the models are different. It turns out it favors model 2 with the lower AIC over model 1 with the higher AIC. Here's the same test for the Bayesian information criterion. And notice in this case that the 95% confidence interval contains the value of 0. So for the BIC, or the Bayesian test, the two models are not different in their fit beyond sampling error. And that contradicts the AIC analysis as well as the likelihood ratio test up here. Now, it turns out that the Bayesian information criteria has a slightly more stringent penalty function for lack of parsimony in the model. And Model 2 has more paths in it than Model 1, and it's getting penalized enough so for that non-parsimony, enough so that we don't have a significant difference between the two. In this case, I would probably conclude that Model 2 probably does fit the data better than Model 1, but I would keep in mind the BIC test, which gives me just a little bit of hesitation about that conclusion. Okay, so let me close this out and come back up here, and that's it. Thanks.